Typical machinery components can indicate misalignment. The waveform data is busy with impacting, but has an underlying sinusoidal waveform, which is the frequency of shaft speed. The data from the horizontal measurement of the 91-tooth gear also shows sidebands around 2 times gear mesh frequency, spaced at 1 and 2 times its shaft speed. Gear misalignment is similar to misalignment of other common machinery components. There can often be a high 1, 2, or 3 times shaft turning speed peak. In the case of gears, the misalignment can also be at 1, 2, and 3 times gear mesh frequency, modulated by shaft speed sidebands. It is very common for the 2 or 3 times gear mesh peak to be higher than the 1 times gear mesh peak. Backlash is the amount of clearance between adjacent teeth while 2 teeth are in contact. Too little clearance can cause the teeth to hit when the tooth deflects due to heavy loads. The teeth should have enough clearance to avoid contact, even when the teeth are at the outer tolerance for machining and when the stress is causing the maximum deflection. When the backlash is too small, oil can become entrapped in the teeth and will be forced out during the meshing action. This oil squirts out with a high velocity, impacting the case and exciting its natural frequencies, causing a loud noise in the gearbox. This is especially true in high-speed gearboxes where relative tooth velocities can exceed 180 feet per second. When a gear train is running with no load, the teeth can slip back and forth, impacting each other. A cure for this is simply to increase the load of the machine. The hitting on the back side of the teeth means 2 impacts are made for each tooth and will result in a 2 times gear mesh frequency. These impacts excite the gear natural frequency and cause it to appear in the spectrum with sidebands of the shaft speed. There may be multiple sidebands around the 2 times gear mesh frequency. The waveform will have considerable impacting with high levels. The backlash and gear wear data are similar in the fact that they both excite the gear natural frequency, and it may have sidebands of shaft speed. The two differ, though, in the dominant gear mesh frequencies. Gear wear tends to have a dominant 1 times gear mesh, while backlash tends to have a dominant 2 times gear mesh frequency. Transmission error is defined as the difference between the output shaft's location if all the teeth and gears were perfectly placed and the shaft's actual location. Earlier in this program, we showed the best design position and shape of the teeth for maintaining conjugacy. Any variation in the position of the teeth as they mesh is called transmission error. The variations can be caused by misalignment, worn bearings, as well as errors in tooth spacing, imperfections in machining, and tooth deflections due to excessive loading. All of these cause small errors in the transmission, which will show up in spectral data. Most transmission errors will show up as sidebands around the gear mesh, and may show up at the shaft speed frequency and harmonics. Sometimes the effects of transmission error will be sidebands around the gear natural frequency. Earlier we discussed the value of determining the common factor. The reciprocal, or 1 over the common factor, is another location influenced by transmission error. If the common factor is 4, the spectral frequency is 1/4 the gear mesh frequency. If the common factor is 2, the transmission error will be 1/2 the gear mesh frequency, and so on. When there are multiples of gear mesh frequency, there may also be multiples of this fractional gear mesh frequency. In some cases, the half order of gear mesh will show up even when the common factor is 1. This is usually when there is a machining error or spacing error in every second tooth on a gear. The analyst can usually get an indicator of the gear quality by checking the amplitude of this common factor peak. If it is half the amplitude of the primary gear mesh frequency, then there is a serious problem with gear quality. Gears can take an enormous amount of torque, and usually without damage. However, sometimes the metal does fatigue, or the force is so strong, teeth chip or break. This shaft was at a right-angle gearbox, similar to one these gears came from. When an excessive amount of torque was placed on the driven unit, this shaft twisted in two, but the gears were not damaged. When a tooth breaks, there is a pulse that impacts once each revolution. This excites the natural frequency of the gear and may have turning speed sidebands. This should also show up at 1 times turning speed peak for the gear. However, it is difficult to determine the source of this 1 times energy. The key to determining a chipped or broken tooth is to look in the waveform. It will have sharp peaks spaced at a time interval equal to shaft frequency. It is necessary to have a period in the waveform that is long enough to capture this repeat pattern, usually 5 to 10 shaft revolutions. This winder is the one with an improper ratio. The data taken on this point shows many sidebands of shaft speed. There are also peaks spaced at the output speed. The analyst knew some problems existed in this gear drive because of the common factor and tooth repeat frequency. However, the waveform data showed sharp spikes, and 2 of them on the low side are spaced at the speed of the output gear. Based on this and the sharp spikes on the high side that are unevenly spaced, he estimated there were at least 6 broken teeth. The rebuild shop confirmed this at the teardown. Chipped, cracked, or broken teeth excite the natural frequency of the gear, which is modulated by shaft frequency sidebands. A high 1 times RPM is present for the shaft. Use the waveform to determine the source of the peak. Remember to acquire a waveform with at least 5 full revolutions to see the repetitive impacting. The effects of load can be seen in this gearbox, which drives 2 output shafts used to mix the raw ingredients for rubber tires. The raw ingredients are placed on a conveyor in 500-pound batches. 1 batch is dumped in, processed, and out before the next is dumped. This means the load on the gear drive varies from one extreme to another in a matter of seconds. The data was collected and stored on a digital audio tape, so it can be played back live to view the spectrum and waveform in the analyzer. The data we will view is from the input shaft, which has a speed of 1185 CPM, or about 19.88 Hertz. The gear has 24 teeth, so the gear mesh frequency is 474 Hertz. Watch the area around 474 Hertz closely. Notice that we can hear some variance in the sound as it is modulated. The sound level increased because a new batch is being dumped in. A peak is climbing out of the noise floor of the spectrum. This is the gear mesh frequency. Notice that there are no sidebands of much amplitude. The only peak is the gear mesh frequency. The load put into the system by the batch substantially affects the amplitude of the gear mesh frequency. If the gears were in good condition before the batch of rubber went into the mixer, they must still be good even though the gear mesh frequency grew. Because the load so drastically affects the gear mesh frequencies, it is important to collect all the data with the same load conditions. Since the load tends to amplify the frequencies, it is best to collect the data when the machine is in load. Gear problems can be a challenge to analyze, but the most common problems, gear wear, misalignment, backlash, transmission error, and chipped or broken teeth, should be recognizable when you have good data. Be sure to take into consideration the effects of load. We have seen the various types of faults that can be determined with vibration analysis. Now let's set up measurement points and choose the best locations to acquire this data. The previous program, Data Collection Techniques, discussed the best measurement point locations for gearboxes. Here we will consider the whys and how-tos for the best gearbox measurement point locations and measurement point setup. Gearboxes have high-frequency occurrences that require exceptional data collection for proper analysis. Some high-speed compressors, for instance, have an input speed of 60 Hertz, turning a bull gear with 256 teeth. The gear mesh frequency is 15,360 Hertz, or over 900,000 CPM. This fundamental gear mesh frequency is above the limits of some analyzers. For others, the second multiple of gear mesh frequency is beyond the capability of the analyzer. Even when the analyzer can process frequencies this high, the first gear mesh frequency of this compressor is well above the linear frequency range of most transducers. A special transducer will be required, which is linear in these frequency ranges. Collecting data for these high frequencies requires special mounting techniques. Most magnet mountings provide linearity to only about 2000 Hertz. Using a coupling fluid between the magnet and sensor and magnet and machine can increase this up to 5000 Hertz. This is still only 1/3 the needed range to acquire information around 1 times gear mesh. A threaded stud mounting with a coupling fluid can increase this range by at least 2 times. Fortunately, not all gear drives have such high frequencies that must be monitored. Many speed reduction gear drives have frequencies that can be monitored with a non-specialized sensor and a good magnet with a couplant fluid. For example, this gearbox has an input speed of 20 Hertz and has 24 teeth on the shaft. The 20 Hertz times 24 teeth yields a gear mesh frequency of 480 Hertz. If we extend past the 3 times gear mesh to pick up any sidebands around it, say 3 1/4 times gear mesh frequency, the maximum frequency is 1560 Hertz. These frequencies are accessible using a good sensor and rare earth magnet or 2-pole magnet. The need for a special sensor usually occurs when the gear drive is a speed increaser. Let's take a look at the frequencies of interest to us on gear drives. If we have an input speed of 60 Hertz and 166 teeth on the gear mesh frequency is 9960 Hertz. We want to see at least the second multiple of gear mesh and 5 or 6 multiples of shaft speed past it. This dictates a maximum frequency of 20,280 Hertz. If the maximum number of lines of resolution is 3200, then the resolution is about 6 1/3 Hertz of energy per line of resolution. This can help us in the high end of the spectrum to determine the status of gears, but we need to see much more than gears. We are of course concerned with multiples of shaft speed and particularly bearing frequencies. In another program on bearing analysis, we pointed out the necessity of having a resolution at least as high as 2 Hertz per line to be able to accurately diagnose bearing faults. This is more than 3 times the resolution we have available for this gear problem. The solution is to define another measurement point for these lower frequencies. We need to define it similar to a typical spectrum for bearing analysis on any machine, such as a pump, of the same speed. This measurement point would help us accurately diagnose unbalance, misalignment, looseness, and bearing problems. Define this point as you would for any rolling element bearing measurement. For high-speed gear analysis, define a baseband with a maximum frequency of at least 2 times gear mesh plus 5 times shaft turning speed. It is preferred to set the maximum frequency to 3 times gear mesh frequency if it is not outside the limits of the analyzer and sensor. Again, add an additional frequency range to include 5 times shaft speed beyond this to examine the upper sidebands. For narrow band analysis of this frequency range, define the first band to include the subharmonics up to 2.5 times shaft speed. The second band should include the 2.5 to 10.5 times shaft speed range. The third band should include everything from here up to the gear mesh frequency minus 5 times shaft turning speed. Note that the band did not include gear mesh or its sidebands. The fourth band should include the area around gear mesh, including the sidebands. The fifth band includes all the energy above this, including 2 times gear mesh frequency plus 5 times shaft speed. The sixth band should include all the energy from here to the F max, and will include the area around 3 times gear mesh frequency. Some analysts define these last 3 bands in units of acceleration because the gear mesh frequencies can generate large amounts of force, and acceleration is a direct measure of force. For low speed and speed reduction gearboxes, where the gear mesh frequency is less than 600 Hertz, the same parameters can be set. For programs that have the ability to specify more than 6 parameters, The lower frequencies can be defined as a typical bearing measurement point, and simply add the bands for the gear mesh frequencies. Make sure the resolution is about 2 Hz per line, and this measurement point definition can save you the need to make 2 measurements at each sensor location. Specific alarm levels can be set for each band. ANSI AGMA 6000-A88 has established criteria for defining alarm limits for different classes of gears depending on the pitch line velocity. Most analysts who monitor the gear drives in a routine PDM program have good success trending the data for change. A substantial change in the levels for any of these bands indicates some faults are developing and alerts the analyst to do an in-depth analysis. Routine surveys for single reduction parallel shaft gearboxes require a minimum of 1 radial and 1 axial measurement at each bearing location. These panels are merely access panels and do not provide a solid path to any internal web. Do not make measurements on them. However, the bolts are usually good sources of transmission because the threads tend to lock onto the case and carry the frequencies well. Use 2 radial measurements when troubleshooting problems in a gearbox. The extremely high frequencies associated with gearboxes may necessitate 2 measurements being made for each sensor location. 1 measurement would be low frequency, high resolution for detection of balance, looseness, misalignment, and bearing problems. The other reading would be very high frequency to 3 or more times the gear mesh frequency with high resolution for determining gear condition. The direction of radial measurements should be in the line of force of the gears, through the center line of the shafts. As in other measurements, we need to be as close as possible to the source of the energy with a solid transmission path through a web or internal frame to the measurement location, and as close as possible to the bearings actually supporting the gears. This double reduction gearbox is typical of many in industry. Note the bearing support locations. Some of them are on an internal web. Remember that shaft vibration, including gear vibration, is transmitted through these bearings and mountings to the case. It is important to know the internal design of the gearbox to accurately place the sensor on a web reinforcement which transmits the vibrations best. If possible, stay away from voids or hollow castings. When monitoring multiple reduction gear drives, such as this or other complicated configurations, set up the measurement points using tunnel vision. That is, define each measurement point with narrow bands that include only the information you need from that point. The alarms can be set for these individual bands. It is not necessary that the bands form a continuous coverage of the spectral data. Simply define the specific areas of interest that may exclude other gear meshes, other shaft speeds, and other bearings. These multiple reduction and angle gearboxes may require 2 radial measurement locations to be made at each bearing location, as well as the axial measurement. This second radial measurement should be perpendicular to the first measurement and can provide valuable information that may not show up in the other point. Gear analysis can seem complicated due to all the energy in the spectrum and waveform. However, understanding some of the theory and design helps us know the types of problems that can occur due to their design characteristics and where they will show up. For accurate diagnosis, you need to know the number of teeth on each gear, the speed of each shaft, and the gear type. When collecting data on gear drives, be sure to acquire data to include 2 or 3 orders of gear mesh and use adequate resolution to separate sideband peaks. On multiple reduction gearboxes, use tunnel vision to zero in on the desired frequencies so you can better diagnose problems. We are confident the application of the tips and techniques presented in this program will increase your ability to accurately diagnose gear drives. Thank you for selecting CSI for all your technical training needs. We look forward to assisting you achieve success in your future endeavors.